What up, everyone? This is LeetCode 278, first bad version. So we're a product manager leading a team to develop a new product. Unfortunately, the latest version of the product fails a quality check. Since each version is developed based on the previous version, all the versions after a bad version are also bad. So we have n versions, and we want to find the first bad one, which causes all the subsequent versions to also be bad. So yeah, it's pretty simple, right? I'm gonna draw what we're basically doing out in a comment. So we have something like this, right? We have a bunch of versions of the product. Eventually, we're gonna hit a version that's bad, which causes all the subsequent versions to be bad. And we want to find the first bad version. Now, we're only given how many versions there are, right? So technically, to us, initially, it looks something, technically, right, quote unquote, it looks something like this, right? We don't know which versions are bad, which versions are good. And that's where this API function that we have to call comes in. And basically pass in the version number, and this API call will tell us if the version is a bad version by returning true, or if it's a good version by returning false. We have to minimize the number of calls to this API. Now, intuitively, when it tells us that we have to minimize the number of calls to the API, right? Intuitively, you should kind of understand, or just kind of generally know that we have to use binary search, right? Because these versions are essentially sorted, right? Because we can't have a good version after the first bad version, right? So all the good versions and all the bad versions are going to be separated out, right? In kind of their own little, quote unquote groups, right? Like we're not going to have good versions scattered over here, but some bads over here, right? Right? That's not going to happen just by the nature of the first bad version causing all subsequent versions to also be bad, okay? Now, I'm going to run through an example, okay? Again, we're just going to use binary search for this. It's going to be pretty simple. So left pointer is going to be here, right pointer is going to be here. We're going to calculate the midpoint. Call this API function his bad version, okay? Now, again, and let me just go in a little bit more detail. Why use binary search, right? Because it helps us minimize the number of API calls, because if we go here and we're at a good version, this version and everything before that is irrelevant. We do not care about it. We don't even have to look at them because we only want the first bad version. Likewise, let's say this was a bad version. Everything after that is irrelevant because they're not going to be the first bad versions, right? That's why it's important that we use binary search to minimize the number of API calls, okay? So now let's go to the next iteration, right? Or first, sorry, let me finish my explanation for this. So this is our midpoint. This is the good version. This version and everything before that, irrelevant to us. We don't care about it. So our left pointer is actually going to go from being here to being one to the right of the right pointer, in cases where the midpoint is a good version, right? We're going to have something like this. Our left pointer's here, right pointer's here. Calculate the midpoint. This is going to be a bad version, okay? So our right pointer goes directly to here, right? Because we don't care about anything after that, right? We don't put our right pointer here because for all we know, this could be the first bad version, okay? So our right pointer goes directly to the midpoint. Now, next iteration, okay? Our right pointer is here, right? Initially, our left pointer is here initially. Calculate the midpoint. And let me we already know that this is a bad version. Now calculate the midpoint, pass that into the API call. It's a bad version, okay? So our right pointer is going here, okay? So we have some like this, right? Right pointer is here. Sorry, when I copy and paste, sometimes it runs the code, or it runs my code. Obviously, we don't have anything in the code, so it's not gonna give us an error. Our left pointer is here, right pointer is here. Now the midpoint, right, we round down. Our midpoint's going to be here. Pass that in. Guess what? This is going to be bad version, right? So our right pointer gets shifted to that midpoint, right? So we have something like this. Now our left pointer and our right pointer are equal. So in our kind of while loop, when our left pointer is no longer less than our right pointer, right, which it wouldn't be in this case because they're equal, we break out of the while loop and we return the left pointer, which in this case would be this version, which I think is the 7th, right? 2, 4, 6, 7, yeah. And the 7th version would be the, in this particular example, would be the first bad version. And so that's kind of how our algorithm works. Yeah. Sorry if that was a little bit slow, but like I just want to make sure you conceptually understand how we're approaching this problem and how the algorithm works rather than just writing the code. Because if you don't quite grasp what we're doing, you might be a little lost. So we have versions 1 through n, right? So our left pointer is going to be equal to 1, not to 0, right? There's no such thing as a 0th version. Maybe in, maybe in certain products outside of this problem, right? In the real world, maybe there's, version 0.1 or whatever for, I don't know, a beta version or something. But yeah, in this problem, all versions start at, the first version always starts at 1. Luckily, this problem's not too difficult, right? Because we have one version, version 2, version 3, right? It's not like a floating value, right? It's not like you have version 1.2, 1.5. So it kind of makes this problem a little bit easier that all versions are discrete, right? And not continuous. So our right pointer is going to be equal to n, right? Because there are n number of versions. Okay. Right here we're just setting the pointers, left pointer, right pointer. Okay, so we're gonna say while left is less than right. Now let's calculate the midpoint. We're gonna say mid is equal to right plus left. We're gonna round down, right? Because if we have two elements, for example, the midpoint, right, would be what? 2 plus 1 is 3, 3 divided by 2 is 1.5. Yeah, that's why we round down, right? 1.5, there's no such thing as like version 1.5. Like I said, all the versions are discrete numbers, which in some ways makes this problem easier. So we're going to say if is bad version, right? This is our Boolean function, and we're going to pass the midpoint. Okay, if the version is bad, right, what do? If the version is bad, we set our right pointer equal to that midpoint. Okay, we went over that in the example. Now, else, this else is going to be, I can just comment it. Cases where the version, it's a good version. Now, in cases where it's a good version, our left pointer is going to be set to the midpoint plus 1, right? Because we don't care about that particular midpoint, which is a good version, or anything before that. So we're going to set the left pointer to 1 to the right of the midpoint, okay? And so this is going to keep running until the left pointer is no longer less than the right pointer, which is essentially going to be where we find our bad version, our first bad version. And, this problem I don't think is too difficult because, yeah, bad. There's always going to be a bad version that's going to be greater than or equal to 1, but also less than or equal to the n number of versions. So yeah, we don't really have like any like crazy edge cases we need to worry about. So it kind of makes our problem easier in many ways. Yeah, they don't have too many like crazy edge cases, so it kind of, you don't have to handle those crazy edge cases, which is good for us, right? So yeah, this problem isn't too bad really. You just kind of need to understand kind of how to approach it, which is using a binary search. And of course, like I said, binary search is super easy, right? It helps us minimize our number of calls to the API because we can kind of just chuck away half of our versions. Or if we go to the midpoint, we can chuck away half of the versions at a specific point if we're at a good version, right? Because we don't care about anything at that midpoint or before if it's a good version. And so approaching the problem in this way helps us minimize the number of calls to the API. So yeah, I hope this was helpful. And yeah, I'll see you in the next one.